Section 4.4, Part 1, deals with the first fundamental theorem of calculus. And basically that's just an introduction to definite integrals. So a few things you need to know about definite integrals are that they have limits of integration. So you can see them, you can tell when you're dealing with one because you'll have numbers here and here. The answer will always be a number unless you're dealing with the second fundamental theorem of calculus, not variables, typically. So that means there won't be a plus c at the end. And I think we talked before about when you evaluate these, like if you put the c, it always gets subtracted back out anyway when you evaluate it. So there's really no sense in dealing with it. But if you put it there, it'll disappear. So you can't really go wrong there. What a definite integral does is it calculates the area trapped between the graph of the function, the x or y axis, depending on the variable of integration, and the lines formed by the limits of integration. So usually this is known as the area under the curve problem. And here's what it states. The fundamental theorem of calculus states that if you take the definite integral from a to b of a function with respect to x, that it will equal f of b minus f of a, where that capital F represents the antiderivative of little f. So we're just going to look at some examples. For these two examples, I picked, if you'll look on the upper one, we're integrating the same thing, but between example 1 and 2, I reversed the limits of integration. So I'm going to pause and let you guys try to work these and see if you can get them right, and see if you can notice like what relationship these two integrals have to each other. So for this first one, when we integrate, the x becomes what?
1/2 x squared.
1/2 x squared. So x squared over 2. And we're going to evaluate it from -3 to 1, which basically means we're going to substitute the top number in first. So that 1 squared would be 1/2. Minus, if we put in -3, that would be positive 9/2. So this is our f of b, this is our f of a. And what is 1/2 minus 9/2? -4. So the question is, what does it mean when we get negative for a definite integral?
That's the area.
It is the area, and typically we don't have negative area, but remember that this may not be representing area. It could be representing like distance, and so negative could represent like a negative direction versus whatever. So you can have negative areas. And what it really means graphically is this. I'll show you. If we graph the original y equals x there, graph y equals x, and we go from -3 to +1, this area is negative, this area is positive. So you can see that, you know, the net result there is still negative. So anything trapped below the axis is going to show up as a negative with a definite integral, and any area trapped above the axis is going to be positive. And so you should be able to look at a graph and kind of tell whether you should expect a positive or a negative answer. Let's see what happens when we integrated from 1 to -3. Now this is very atypical. Typically, the smaller number will be here and the larger number here. It's pretty rare to reverse the limits of integration, but it can be done, and I want to show you what it does when you do that. We have the same integral, x squared over 2. This time we're evaluating the b is -3 and a is +1. So when we substitute in, we get 9/2 minus 1/2. Remember, it's always top minus bottom here. F of b minus f of a. This is a, this is b. So this time we get +4. So see how we got the same number but the opposite sign? That's what will happen anytime you reverse the limits of integration. So if you work it once and then you reverse the a and the b, you should get the same number but just the opposite. Okay, so for this example, we have the integral from 4 to 9 of the square root of x dx. And in order to integrate that, we first need to write it in exponential form. So we really are integrating x to the 1/2. If we add 1 to the power, we have x to the 3/2. Divide by the new power is really 2/3. So 2/3 x to the 3/2. Now, we don't have to put this back in radical form, but what I've found is people actually seem to do better with radicals at this point rather than, fractional exponents. So if you want, if it helps you to see it and evaluate it, you can write this as the square root of x cubed. It might make it a little easier for you to substitute in. So if we put the 9 in, we get 2/3 times the square root of 9, which is, what's the square root of 9? 3, and 3 to the third is
9. No.
27. 3 to the third is 27, right guys?
Right.
Okay, so we have 2/3 times 27. This is f of b minus f of a, which is 2/3 multiplied by the square root of 4, which is 2 to the third, which is 8. So really we have 18 minus 16/3, which equals what?
38/3.
38/3. What is that as a decimal?
12.6 repeating.
12.6 repeating? Okay. I want to show you something on your calculator right now. So we'll pause a second and let everybody get their calculator. And I want you to type into y equals the original function. So I want you to type into y1 just the square root of x. So everybody kind of do that. And then just do a standard zooming window, zoom 6. And we'll talk about a way to check these in your calculator. So if we take our calculator and we put in the original function, you have to be really careful. Make sure it's the original, not the integral. So here I've typed in y equals the square root of x. And the only thing, there are a couple of limitations on this. It has to be able to see what you're integrating. So like if we're going from 4 to 15, you can't, the standard zooming only goes from -10 to 10. So you may have to adjust the window, to see beyond that and check it. Do y'all understand that? So you would have to go to window, and check it. But we're going just from 4 to 9, so this is fine. But if we were going from like 4 to 15, we would need to go and adjust like our maximum x here. And we would also need to adjust our y's. You'd have to make sure you could see enough of the graph. If it can't see it in that window, it can't calculate the integral. So here we are. We're going to just do standard zoom because that should be enough for us. Zoom 6. All right. Now if you go to second trace, which is the calculate menu, do you see number 7? Okay. So come down there to number 7, and we're going to calculate the integral. And it's asking you for your lower limit. So what was my lower limit? 4. Okay, so my lower limit was 4. And you just hit enter. And what was my upper limit? 9. So x should be 9 for my upper limit. And now hit enter. And it will give you the rounded there, but you can at least check it. So that's one thing I like about definite integrals is you can check them in your calculator if you can get a zooming window that will kind of let you see all of that graph. And it'll even shade it for you so you can get a visual on what it was that you've calculated. Any other questions about this one?
Wish you would have showed us that.
No?